This is Professor Nathan Smith, Fresno Pacific University. I'm recording this video from my economics and business class to explain how to run regressions. I'll start with the regression that we ran in class on Wednesday night. And this was based on Chapter 6, Problem 1 in the book. They gave us data on gasoline sales, which I've copied into the column here. There was also a time trend. There was 16 quarters, so it was started in 1995, 1996, 1997, 1998, 4 quarters in each, total of 16 quarters. So, the first thing it asked us to do was to calculate a time trend, so I'm going to show you how to do that. You do this by running a regression. Start with the data analysis, data ribbon, data analysis button in that ribbon. And pick regression from this list. Then pick the input y range. So that will be, in this case, y is the variable that you're trying to explain. So we're trying to explain gasoline sales. We're trying to explain gasoline sales as a function of time. So we select that time. And then we fall through by running the regression. Okay, now I've already generated this regression, and so I'll use my version of it. So we take this 2902.55, 117. These numbers actually come out slightly different than me. I probably copied a digit differently somewhere, but that doesn't really matter. It's very close. So I recorded this as the formula. So this is the intercept. Notice GT, so the gasoline sales, estimate of gasoline sales at time t, is the intercept plus the coefficient times t. Okay, let's go back to data. I don't need this. So, look at data. And I've actually generated this, so I used that intercept, used the coefficient, and then calculated this linear trend. Notice that I just used the same formula for the entire column. The only thing that changes is this B17, so it's changing, it's picking a different time, but everything else is staying the same. Okay, now we can look at this in a chart. You notice this chart includes the linear trend and the log linear trend, which we'll calculate next, and the two trends look almost exactly the same. You notice it isn't a particularly good match for this data because there's an obvious pattern in the data which our trend is not picking up. Clearly there's seasonal variation in demand for gasoline. I guess if we were to fix the minimum of this scale at 0, then it looks a little bit closer, but this stands out more, so I'll just leave it at that. Okay. Well, next it requested that we calculate the log linear trend. So log linear trend, for that we have to run a different regression. We basically substitute a different variable to be explained. The variable to be explained is the log of gasoline sales. So first of all, let's look at this formula. This is just the log, natural logarithm of gasoline sales, dragged all the way down that column. Okay, so once again, data tab, data analysis button, regression, okay. But now instead of gasoline sales, we're going to try to explain the log of gasoline sales. Input X range is the same, it's the time series. We generate this data, and I've already done the same regression, so it's this, again, let me go into this a little bit more. This R squared is somewhat important. This tells you how many, what percentage of the variation is explained. 42%, not that much. That's because we're missing the seasonal variation there. You've got this intercept here. And the intercept turns into a coefficient this time, but to transform it into the coefficient, we have to put this exp function which reverses the logarithm. So we estimated the logarithm of gasoline sales, and now we're going to calculate gasoline sales from the logarithm of gasoline sales. exp, which is e to the x, is the inverse function, so that gives us our coefficient. And then here we don't need to transform this because, well, we sort of transformed it. 1.0049, this is just the same thing with a 1 put in front of it. This is a growth rate. We take it to the power of t. So the growth rate, each period, it grows by 0.0049. So when you stack all those on top of each other, it'll be 1.0049 to the power of t. Okay, so go back to data. The log linear trend, this formula is just plugged in. Notice as we go down the column, we go from B2 down to B17. Gives us a bunch of values. These are all a little bit greater, slightly greater than linear, but they're actually pretty close together. And if we look at our chart, then we see those lines are almost on top of each other, so there's really not much of a difference, and neither of them pick up the seasonal variation. So if we wanted to improve that regression, we could just put dummies in for seasons, and then we'd probably get a fairly accurate, a much more accurate representation of that data. But what I wanted to do next is something a little different. This is not a log linear regression, this is data. Okay. Oh, right. Data 2. Okay. So, with this regression, it seemed a little bit pointless to run the log linear regression. You saw the procedure, but since it generated almost exactly the same result, and you may not see why you would want to need to know how to do that. So that's why I wanted to construct a different data set where calculating the log linear relationship is a little bit more valuable. So I just generated this data randomly by a certain procedure, which never mind, don't worry about what that was. But it's charted here. So again, it's sort of a time trend. And you can see how the variables changing over time can be a good deal of fluctuation. In fact, if I wanted, I guess I could link these. Let's stick a solid line in here. We'll keep it thin so it doesn't clutter the graph too much. So there you can see there's this time trend here in some variable. Never mind what the variable is. Okay, so now what we want to do is, first of all, let's see how well we can fit this data with a linear regression. So again, we'll data tab, data analysis button, regression, okay, and then we pick the input y range, which in this case I've got 100 variables or 100 observations here, and the time range, which is b. Scroll down to here. Okay. So this is what I'm trying to explain, y. This is what I'm trying to explain it with, x, which can be interpreted as time, and then let's call this linear 2, so a linear regression for data set 2. Now what's our formula? So insert a formula, an equation, and our equation will be 1374, getting it from here, 1374.803 plus 299.1806 times x. So y equals, and let's call this y maybe this doesn't have that function. Okay, never mind, doesn't matter. So y equals, this is our estimate for y. In fact, we can take this asterisk out because that looks better. Okay, so this is our formula. And we're going to introduce it over here. So let's drag this over, give it some room. Okay, so y time trend, we call this. Okay, so y time trend equals start with our linear 2, our intercept, plus 299 times x well, I already got those dollar signs on them. Okay, that's good. I wonder how I did that. Anyway, okay, so here's our time trend. And let's see how well that fits. We'll add another series. Y time trend. Series value. So for Y, it'll be this. For X, it's once again time. Let's call this true Y. Alter that. Okay, and this is an ugly way of representing this, so let's remove the markers. Put a solid line in there instead. We'll make it red. We'll make it kind of thin. That's too thin. Okay. So, okay, there's our Y time trend. Well, I mean, if you look at the R square, that's actually pretty close. It explains 93% of the variation. Not too bad, but if you just look at this with your eyeball, you know, it's clear that's not really what the data is doing here, right? That's not really a very good description of how this particular data is behaving. So let's see if we can do better. So let's do Y log linear time trend. Maybe a log linear will be a better description of what's happening with this data. Okay, so I've already calculated Y, or lin Y. So that's this column. So now what we want to do is run another regression. Data analysis, regression. And then this time for our Y range, we'll input lin Y. Okay, we'll rename this sheet log linear 2. And what does it tell us? Okay, first of all, t-stats are highly significant, so clearly, yeah, and we explain a lot more of the variation, 98%. So now we're getting a pretty good fit. And so what's our formula? Let's insert an equation here. The formula will be Y equals, actually, hold on a second. So first of all, we need to calculate something called coefficient, and we'll make this equals exp. I explained this before, why you want to do this. Exp and intercept. So why that inverses the logarithm that we took initially and gives us a regular value. Okay, now we want to multiply 5382.22 times 1.019157, I guess, why not? We'll just put it this way, to the power of x. Oh. Okay, good enough. I'm not using my equation tool, but that's okay. This is good enough. Okay, so that's the formula we want to use. So in our data here, we'll calculate this as, so I just pressed shift and then highlighted that square and put it in dollar signs, times 1 plus and then that to the power of x1. Okay. Okay, now, well, let's spread this legend out a little bit so it doesn't look quite so messy. We'll add another series here. Add a series we'll call y Loglinear time trend. And now the y values are Loglinear time trend values, and the x values are time values. Okay, let's clean this up a little bit. We don't need markers, we'll use a line instead. Let's make the line bright blue. And we'll make it kind of thin so it matches the other one. Actually, that's too dark. Make it line color. There we go. And I think you can see this fits the trend much better. A much better fit for this trend than the red line is. So that's basically why you want Loglinear to know how to calculate Loglinear trends, because a lot of times the data will have this form. And when it does, you will not make very good projections using this linear time trend, but if you use the Loglinear time trend, that will work somewhat better. So that's a brief introduction to regressions. Hope that's clear.